All right, so this is going to be our polar coordinate notes, and I'm just going to go ahead and get started with a warm-up. So this says convert the set of parametric equations to rectangular form, and it has your x of t and your y of t. Remember, the first step to any of these types of problems is to solve for t, and then you can plug it into the other function. So I'm going to go ahead and solve this x function for t. So this x is equal to the natural log of t minus 1. Okay, and I'm going to go ahead and solve for t. So the first thing I have to get rid of is I have to get rid of this natural log function. So in order to get rid of that, I'm going to use its inverse e. So I'm going to say e over here, e over here. So basically put all of this side into the exponent, put all of this side into the exponent, and the e in the natural log will cancel out, so that I'll have e to the x is equal to t minus 1. Then I'm going to move over the 1, so I'm going to have e to the x plus 1 is equal to t. There we go. Now that I have t, I'm going to go ahead and plug that in to the next function. Okay, so I'm going to plug this in for this t here. So then I'm going to say y is equal to 3, big blank for t, plus 2. And in the blank, I'm going to put e to the x plus 1. Okay, guys, you have to use parentheses, right? If you don't use parentheses there, what would not happen? You would not distribute that 3. So be careful, you have to put parentheses. So then I'm going to have 3 e to the x plus 3 plus 2, which is just 3 e to the x plus 5. Okay, the next thing you should really think about is domain restrictions. So remember, to tell if this function has a domain restriction, you should go back and look at your x function. What's the question you should ask? What is the range of my x function? Okay, because the output of your x's is all the possible x's, or all the possible domain here. Okay, so I have to think about the range of this function. Well, this is a natural log function, so it's going to look something like this. It's not perfect, but it's going to look something like this. And so this has an infinite range, which means that this function has an infinite domain. So there will be no domain restrictions on that one. All right, next one. This says sketch a graph of f of x is equal to e to the x minus 2 plus 3 without using a calculator. Use the graph to evaluate the limit as x approaches negative infinity of f of x. So in order to graph it, the first thing you need to think about is the parent function. Okay, the parent function looks kind of like this. Okay, with a turning point at 0, 1. That's just normal e to the x. Okay, or really that's any normal exponential growth. So that's what it looks like. So now I need to think, how is this going to affect, or how are my transitions going to affect this graph? And anytime you're trying to graph a transitioned or a transformed exponential graph, there's always 3 steps. Okay, the first step is always determining growth or decay. Growth or decay. So in order to determine growth or decay, I'm going to look at the base of my function and decide if it's greater than 1 or not. E is greater than 1. Therefore, this is going to be growth. Okay? And remember, for exponential functions, growth just means that it's going to go up on the right-hand side, or away from your asymptote on the right-hand side. All right, the second thing you have to go find is your asymptote. Okay, so in order to go find your asymptote, you need to go find one of your transitions. Let's think about it. What was our asymptote on the original parent function? It is y is equal to 0. Okay, and if we think about this, if I move this function left and right, nothing changes, right? The asymptote is still technically in the same spot. But if I move it up and down, the asymptote value changes. So when I'm looking at my function, if I'm thinking about where has the asymptote moved to, I'm going to have to look at the up and down. Oh, whoops, wrong thing. Do not want to pick that one up. So I'm going to have to think about not the up and down. Why is it doing that? Not the up and down transition, but okay, sorry. Not the left and right transition, but the up and down transition. Okay, so I'm going to look at the up and down transition, which is a positive 3. So that is going to give me y is equal to, what happened? I moved up 3, so this is going to be positive 3. All right, and then finally, I need to do the turning point. Okay, for turning point, you just take your parent function turning point, which is 0, 1, and then you're going to transform it with whatever transformations are up here. So you would do any vertical stretches or flips first, or any horizontal flips as well, but because we don't have anything to multiply by, I'm just going to move it. So what does this tell me? This tells me I'm going to go right 2, and this here tells me I'm going to go up 3. Remember, anything on the outside of your exponential natural log is an up and down movement. Anything on the inside is a left to right movement. So I'm going to move it right 2, down 3. Up 3. There we go. So I'm going to move it to 2, and then I'm going up 3, so 4. And then I can go ahead and graph it. So when I'm graphing it, it'll look kind of like this. Turning point at positive 2, positive 4. Asymptote at y is equal to 3. And then it's growth. So my function should go away on the right-hand side and towards the asymptote on the left-hand side. That should be more curved. It should be going towards the asymptote. It should never touch the asymptote, but should be going towards it. Oh, one more thing on this one. It says, use the graph to evaluate the limit as x approaches negative infinity. Well, so this is saying what's happening to your y value as your x value goes further and further left. Well, what's happening? So the limit as x approaches negative infinity of this function is equal to, what is it getting closer and closer to? We just talked about that. It's getting closer and closer to the asymptote. Where is the asymptote? Positive 3. That would be our final answer. All right, this says sketch a graph of f of x is equal to the natural log of x plus 3 minus 2 without using a calculator. Use the graph to evaluate the limit as x approaches negative 3 from the right-hand side. So many students get confused about this little plus. It just means from the right-hand side. So you're going to approach your destination from the right-hand side. It'll look like that. So and this is the part that kind of confuses students. So technically, if this is where we're headed, and you're coming from the right-hand side, you're going left. So, but don't let it confuse you. Just start from whatever direction it has, so the positive direction, and go towards your destination. All right, so again, I'm going to go ahead and think about what is the parent function. Well, the parent function for logarithmic growth looks like this. Okay, with a turning point at 1, 0, and an asymptote at x is equal to 0. All right, it is going to follow the same 3-step process. First thing you have to decide is growth or decay. All right, when you're deciding growth or decay, you're going to look at the base of your logarithm. If it's natural log, it has a base of e. We've already discussed e is greater than 1, therefore this will be growth. What does it mean to be growth? It means that after your turning point, the top side will go away from the asymptote. It'll go away from the asymptote. All right, next thing we need to talk about is the asymptote. All right, the asymptote is going to be our transition. Again, we need to think about, oh, it's not going to pick up the whole thing. Can we will that work? Yeah, that works. Okay. So again, we need to think about what type of transition will matter. An up and down transition is going to keep your asymptote in the same spot, okay? It's a left to right that'll actually affect your graph. So I'm going to now choose the left to right transition. So what did I do? I moved left 3. So then my asymptote will be left 3 from 0, so negative 3. And then we'll do our last step, the turning point. Okay, my original turning point for a logarithm is 1, 0. And then I'm going to do my transitions. Again, you would multiply anything in first. We don't have anything to multiply, so I'm just going to move it left 3 and down 2. So that'd be -2, -2. And then I could graph that. All right, so that's my turning point, and as we discussed, the asymptote is going to be at x is equal to -3. And then when I'm graphing my function, it's growth. So it'll go away from the asymptote on the top side and towards the asymptote on the side below the turning point. And then let's talk about what the question asked. The question asked, what is the limit as x approaches -3 plus? So from the right-hand side. So -3, this is my destination. I'm going to approach it from the right-hand side. So I'm going to be going like this. So I'm going to start on the right-hand side and approach it, and I'm going to follow my graph. What happens? We go down, 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 down. So my final answer will say the limit as x approaches -3 from the right of our function is equal to -infinity. Of course, you could also say does not exist because anytime a limit equals infinity, it does not exist. All right, Alma brought a laptop computer at a store that gave 20% discount off its original price. The total amount she paid to the cashier was P dollars, including an 8% sales tax on the discounted price. Which of the following represents the original price of the computer in terms of P? Okay, so for this, what we really have is we have two variables. We have the original price and we have P, the amount that she paid. So whenever you're calculating sales, for instance, if you have 20% off something, sometimes it's easier just to figure out what 80% of your current price is. So that's kind of something to take in consideration because you can kind of see that's what they're doing here. There's a lot of 0.8s up here, and you can kind of see that's what they're headed towards. So just so you know, right, the same thing, if something is 20% off its original price, that means you're paying 80% of the original price. So for instance, if I want to say just the discount, I would say take P, and I'm going to say original, I'm going to call that just W. You don't want to make it O, right, because it's too close to 0. But so I'm going to say P is equal to the original times 0.8. But then after that discount, she then had to pay sales tax, which is 8%. So again, instead of saying 1 plus your original price times 1.0, you don't, oh, sorry, you don't want to say, that, right? That's too complex. What's much easier than that? W times 1.08, and it works the same way because you're tacking on, you have your original price, that's in the 1, W times the 1 is just your original price, and then you tack on another 8%. So it works out really nice, especially if you're trying to calculate tax. Again, it's one button in your calculator instead of two. So I'm going to multiply this by 1.08. Now, here's the thing, it wants an expression for, or so which one of these represents the original price. So I'm going to go ahead and solve for W. What do we get? We get P over 0.8 times 1.08. And that would give us this guy right here. Alright, so that's it for the warm-up. Now we're going to move on to the polar coordinates. So this says points are written in the form r theta. R is the directed distance from the origin to your point. So this is almost like magnitude if you're thinking in vectors. It's the direct distance from the origin to a point, especially if you're working on the position vector. And then theta is a directed angle, like your direction angle, counterclockwise from the polar axis. So guys, we've kind of worked with this before at just various times, but the whole point of polar coordinates is that sometimes it's much easier to have, like if you are, again, kind of like the submarine that we talked about. If you are the submarine, it's much easier and almost better for you and your crewmen to know where you exactly are in coordinates to everything else, right? And then if you're working in that kind of thing, you can kind of make this nice circular map, okay? And you can say, okay, there is I don't know, there is a whale or something, and it's this far away, and it's got this direction angle from the helm of the ship, right? You could say something like that, and that might be way easier than trying to figure out the latitude and longitude for everything all the time, and it's much easier than moving around your origin for the rectangular. So it does have its purposes in, well, not, of course, not just radars, but you can use polar for pretty much any type of system that is circular. So you can keep that in mind. So when we're writing polar coordinates, again, there's two major pieces. There's r, which is the distance, and there's theta, which is the angle. Okay, this is very different. We used to have x and y, okay? This used to be your rectangular point. This is a polar point. Okay, and if you think about it, it's and like, here's how I like to memorize it. It's a lot like vectors, right? You have your magnitude and your direction. It's a lot like that. And you'll find there's actually several commonalities to vectors here. So you can kind of use that knowledge to your benefit. All right, so let's go ahead and try one. So I'm going to go ahead and do this one first. It says plot each of the following points in polar coordinates and gives us the point 2, pi over 3. So 2 is the r, that's the distance from the origin. So if this is the origin, right here, then what's happening is, you see how these circles coming out? These are all circles that have the same distance from the origin, right? This circle has a distance 1 from the origin. This circle has a distance 2 from the origin. Next one that has a distance of 3 from the origin, and so on and so forth. So if I want a distance of 2, I should be on this second circle. Okay, the second circle away from the origin because it has a distance of 2 from the origin. All right, so I know my point will be somewhere on this circle. Then I need it to have a direction angle of pi over 3. So I'm going to start from the initial side here and go until I'm pi over 3 away. Now, that's not pi over 3 right there, but here's how we're going to count it. This does not look like your typical unit circle, right? What does your unit circle typically have? It has 3 lines. It has pi over 6, pi over 4, pi over 3, and then goes to it. Notice we have more, okay? So this circle, if you count them up, how many lines do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so all together, this pi, 1/2 of my circle, pi, is cut up into 12 pieces. Okay, so each of these are pi over 12. So if I want to count them, I can say this is pi over 12, this is pi over 6, this is pi over 4, pi over 3, and then this right here is 5 pi over 12, and then pi over 2. So is it a little bit different? Yeah, but it's kind of more useful because you can plot more different types of points on there. So I'm going to go ahead and plot my point. So my point is supposed to be on the second circle at pi over 3. So this is the direction, this is the correct circle, and I'm going to plot the point. All right, next piece. This says 3 negative pi over 6. So that means I need to be on the third circle on my way out. And then negative pi over 6, let's see, this is negative pi over 12, this is negative pi over 6. Make sure I'm on the third circle. And there we go. All right, and then negative 2 pi over 3. So no, there is no negative second circle on here. I'm going to choose the second circle, and you're going to see how I'm going to kind of fix this here in a moment. So this is 2 pi over 3, which if I translate that into 12ths, this is going to be, let's see, multiply by 4, multiply by 4, this is 8 pi over 12. So I can count to the 8th line. This is 6, 7, 8. So this is the 8th line right here. All right, and it wants me to go negative 2. Negative 2. Well, again, there is no negative second circle. So what I'm going to do instead is just cross and go right here. So what did I do? Essentially, if it was positive, I would have plotted it here. Okay, but because it's not positive, I need to cross the circle, and that gets me there. I plot that on the right one. It's almost optical illusion-y. You have to be careful, make sure you're plotting it on the exact one. Yeah, that looks good. Okay, so that's kind of how you'll plot those negative values. All right, this says plot the point given in polar coordinates and find two additional polar representations of the same point. So this is -1, -3 pi over 4. All right, and if I translate this into twelfths, I'm going to multiply by 4, or sorry, multiply by 3, and I'll get -9 pi over 12. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be right here. And it works right because it's pi over 4. So just double check your work there. So this is -3 pi over 4. It's right here. Now it wants a distance of 1, or sorry, -1. +1 would go right here. Okay, +1 would go right there. But because it's -1, I have to go in the opposite direction. And so I will be right there, right on the pi over 4. And speaking of which, let's go ahead and call it that. 1 pi over 4. That's one way to call it. Let's find another one. So instead of 1 pi over 4, I could go ahead and say this is what, so I could go ahead and say that this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could also call it 9 pi over 4. And there's lots of other options. There's infinite possibilities, but those are just two different ways to call it. Here's the next one. This is 5 pi over 2. So 5 pi over 2, let's see, this is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and 5 pi over 2, and it's all the way at 8. So there's our point, and we could of course also call that 8 pi over 2, or we could call it -8 if I call this 3 pi over 2, because that means you would come here at this direction, but instead of going a +8 in that direction, you would go negative. This next one says graph each polar equation. This is r is equal to 3, so I'm going to go out to my third circle. And this is saying the radius is always 3, and it doesn't matter what theta is. So it's going to kind of create a circle equation. Sorry, this is not perfect, but I should be outlining the third circle from the origin. And there we go. So that would be your function. If of course, you should outline it better, but that would be your function. And this says theta is equal to 2 pi over 3. So in this case, again, I need to know where 2 pi over 3 is, so I'm going to turn it into 12. So I'm going to multiply by 4 on both. So this is 8 pi over 12, which is going to put me right here. This is 8 pi over 12. And it always wants it to be 8 pi over 12. Okay, it wants your theta to always be 8 pi over 12. So in order to graph that, I'm just going to make a line. Okay, and so this line is going to start up here and go all the way down. So then we ask ourselves, should we stop or should we continue? We're going to continue because there's also negative variations of this. And there we go. Now you have your nice, beautiful linear line. And that is it for notes today. Make sure that you're looking at your homework packet and keeping up with that. There are some worksheets for some of these things, so make sure that you are checking the website and getting any worksheets that you need. It should tell you in your homework packet if you do need it. And have a wonderful day.